Good afternoon. It's a very cozy audience today, so hopefully I won't bother you too much. If you feel sleepy after, you can come to our booth. We have a nice coffee that you can make up again. So today I'm here to talk about how engineering can help the risking subsea cable installation project. My name is Roberto Longo. I'm a Chief Operating Officer for AVENTA. Just a few words about AVENTA. AVENTA is a French company with almost 15 years in the market. We are around 400 people spread across different offices in France, where we have our headquarters, Italy, Croatia, US, and other countries. Our core business is around offshore energy, and particularly we have an expertise in subsea cable, and we operate at different level with in consulting, where we provide expert to our clients, engineering, where we do engineering studies and projects design, and marine operation, where basically we assist the construction of and installation of cables. This is just a snapshot of our footprint. So we are our biggest hub are in France and Italy, and then, as I said before, we have offices in Europe, US, and Australia. This is just a snapshot of our clients. So we work at different levels, from developer, EPC contractor, cable manufacturer, and others. And we try to operate at different levels, from concept design, detail design, decommissioning. So today I'm just going to briefly touch base on engineering and how this is used for subsea cable. And after that, I will just deep dive in a few key areas, which is the cable protection, the cable installation, and how having a better understanding of the metocean characteristic of your site can de-risk your project. So starting with an introduction, subsea cable are representing typically 5 up to 10% of the capex for an offshore wind farm, but they generate most of the headaches in terms of insurance claim, and if there's something that might break, that's most likely the cable. As you can see this graph, the more cable will be installed, the more cable will fail. Okay, so essentially our task as an engineering company is to assist our clients in de-risking the project, making sure that we reduce as much as possible the risk of failure during the installation and during the operational life of the cable. Okay. So, as I was saying, engineering is a small part as well of the investment. Typically in fixed wind, which is a more robust industry, 3 to 5% of the capex. If you go to floating wind, it can go up to 7, maybe even 10% because of new technology. So if you look at this, it's a small portion of the cake, but if you do engineering wrong, essentially you're going to waste a lot of money later on because of the problem you're encountering. Okay, so we could speak weeks about all the engineering study needed, but today, as I was saying, I'm just focusing on 3, which is the cable protection, installation, and metocean. So starting with the CBRA. So the CBRA, cable protection, cable buoy risk assessment, is a study which is started normally early stage and is defining the strategy for protecting our cable. So the idea behind is that to assess all the risks, external risks that can affect my cable, can be anthropological, like fishing, marine traffic, and others, or it can be natural, like seabed mobility or other aspects, so geohazard and so on. In 2015, Carbon Trust released this guideline, which is well recognized in the industry as a sort of a Bible for cable buoy risk assessment. There have been few new releases since then, but essentially this is drafting the methodology that should be followed for this type of study. Okay. However, as I will explain a bit later, there are some, of course, flaws in the system. So there are few areas where are free to be interpreted in different ways, and this might lead to problem if poor judgment is made. Okay. So let's have a quick look at the methodology. So first of all, we need to agree, all the stakeholders, about what is an acceptable risk. Okay, and this is one of the most critical items because it's part of a big discussion. So the less risk I want to take, the more money I will spend to protect my cable. So it's very difficult to find the balance, what is acceptable and what is not. And also, what is true at the beginning of the project might no longer be true at the end of the project. So I've been in a lot of discussion where a certain risk level was accepted early stage, and now down the detail, everything is rediscussed, and this is creating some issues. So anyway, let's assume we have accept what is our risk level. Then we have to collect all the data. It can be geophysical, geotechnical, and others. We segment the route, so we split the route in areas of similar characteristics, and this is a very vague definition. So again, this is where we start having interpretation. Okay, it's a bit arbitrary what is similar characteristics. Okay, and depending on the segmentation, there will be big impact on the results we are getting. Then we have to identify all the threats, anthropological and natural, assess the likelihood of this event to happen and what is the consequences, so we can calculate the risk. Then we make an evaluation of the risk and ranking. And for any risk which is not in the acceptable area, we need to implement a mitigation to make the risk acceptable. Okay? And after that, yeah, you produce a document which typically is a quite live document. So you start early phase and then you continuously update the document anytime you have new information, until even after the installation, when you know where your cable is sitting, you can review the risk based on the as-built. Okay? What is the mitigation in this case? Typically, if we can, we are going to bury the cable. If you cannot bury the cable, we're going to protect with rock berm or concrete matrices or cast iron shell. There are different ways of protecting our cable, and it depends on a lot of parameters. The way we are going to bury the cable is not part of the CBRA. That will be part of a study like the burial assessment study. And the CBRA is the input to define the strategy for the protection. Okay? So, as I was saying, there are different elements. So I'm just deep diving a bit more in one of the threads, which is the anchor striking. So my cable might be crossing some very busy routing for shipping. And we have to assess what is the risk of one of those ships to drop an anchor on my cable. Okay. Now, typically, we use a probabilistic approach. So we take IS data of all the, density of navigation in the area. We calculate how many crossings we have for each type of vessel on our cable. And like this, we can have a frequency distribution of how many of this type of vessel cross my cable. After that, there is a formula that you see on the screen, which helps us understanding what is the probability of anchor striking. Okay. And here we have a lot of ingredients, which again are left a little bit to interpretation. Okay. So the first point is, in general, the IS data are not always reliable, so that's also another source of uncertainties. And it's very important that all the data are clean, complete, where you are lacking information and so on. All these elements, if you read the definition, they still leave a little bit of room for interpreting in a different way. But today I just want to speak more about the P incident, which is the one having the major impact, which is essentially a probability of incident requiring the deployment of an anchor. So here we're talking about, okay, we have vessel crossing. What is the probability they have an incident, and that incident is making them dropping an anchor, okay? So it's not that easy to assess. So Carbon Trust give us some example. There is a table with some example from literature, and you have a different probability of this anchor to be dropped depending on different scenarios. And each one with different frequencies of occurrences. So depending on which number I select, I can get very different results. So only for the sake of argument today, I'm just showing a real example from a project we work on. So case number 6 is assuming this probability, so a bit less conservative. So a total loss for the ship and is dropping the anchor. The other one is a more likely event, so there is a problem with one of the engine and they decide to drop an anchor. As you can see, the graph on the right is telling you how deep I should bury my cable in each section. And as you can see, for case 6, I only have a few kilometers of cable to be protected. For case 7, actually, I have almost 100 kilometers of cable to be protected. And in terms of cost, we're talking about millions and millions of euros to be spent, okay? So that's why, poor judgment in selection might either lead to expensive projects, or on the contrary, I might, let's say, underestimate the risk, okay? So in general, okay, this is just to touch base on some other, let's say, uncertainties. The CBRA has a lot of uncertainties based on the input we are using, the way we are interpreting those inputs, and some of the decision we have to make during the process. So that's why engineering judgment is fundamental. So in this case, always rely on experienced company and experienced expert that can really help you with that. Okay. Now moving on, the next example is installation analysis. Okay. So if you have to install a cable, we need to understand. Okay, what is the maximum wave I can face without breaking everything? Okay. And how we do cable installation? Well, back in the days, we've been installing telecommunication cables since 1850, so more than 150 years ago. And in the past, it was sufficient to just solve analytically the catenary equation, which is well known from mathematician. And essentially, I just predict how much my vessel might move, solve the catenary, and I can know what is the bend radius, what is the tension, all the things I need to monitor, okay? But things change. I mean, now we are really pushing the limit. So if you're talking about offshore wind or interconnector, we have to install a long cable, a lot of cables. We cannot do it only on the summer. We have to go in the winter time where the weather is harsher. We feel more comfortable because we have more sophisticated way to monitor the cable, so I can really go really close to the limit. We have bespoke vessel and everything. So all of that means that more and more we're pushing the limit. And one important lesson is that dynamic is important, okay? So it's no longer enough just to solve the catenary equation, because there are complex dynamic behavior when we go in harsh environment. This is the same vessel in different weather conditions, okay? The one on the left, 1 meter HS, is what we were facing maybe in the 90s or early 2000, where we could install everything in the summer. Now we have to install even in the winter, and we are trying to achieve more HS 3 meter. So as you can see, the cable dynamic is very complex and need to be properly addressed. So what are the potential risks during installation? Of course, the first risk is not to have enough experienced people on board the vessel. That's a fact. But in general, there are certain things that can be addressed and mitigated in the engineering phase. For instance, the selection of the vessel, the study of how the vessel is behaving to the waves, and how this translates into cable dynamic. So this is the part I would like to discuss a bit more today. So vessel response. So selecting the wrong vessel might lead to failure, okay? So again, here we have the same cable, same environment, 3 different vessels, okay? And the 3 vessels are responding in a completely different way. So on the right side, just to explain, these are the response amplitude operator of the 2 main vessel motion, which is pitch and heave, which are the one more affecting the cable laying, okay? As you can see, the vessel A and B, and the green, let's say, rectangular is telling us, okay, where is the majority of the SEANERGY spread for this specific case. So as we can see, the vessel A and B, they have the natural period within this range of the waves, while vessel C is quite far beyond. So, and this is reflecting the way they're responding. So vessel A, as you can see, is moving quite a lot, and we see quite dynamic behavior at the touchdown. Same for vessel B, although it's not critical. Vessel C is barely moving. So again, selecting the right vessel, or at least know the limit of your vessel, is very important to reduce the risk, okay? Okay, now, how many simulations do we run, okay? So the approach is basically a Monte Carlo approach. We look at the metocean data, we try to select all possible combination of wave height, period, direction, everything that can happen. We run simulation, and we see which simulation give us a pass, so the cable doesn't break, and which one have the cable compromised. So here, just for the sake of argument, I just put in some example, like, okay, three water depth, 9 different HS, blah, blah, blah. I end up with easily with 20,000 simulation, okay? And therefore, it's quite impossible for a human being to open each one of them singularly, check what they need. So that's why automation is important. So we use a lot of automation in Python programming to, first of all, to reduce human error, but most importantly, to digest and interpret all this information. So why installation analysis are important? Well, they help us verifying the procedure, the approach we want to follow to install the cable. They help us identifying the risks. They can help us testing mitigation and identify the weather limit. If the weather limit we find is not what we wish, okay, let's come back to optimizing the procedure and so on and so forth. So we go in the typical, let's say, design spiral, okay? But in general, as any time you use a software, anybody can buy a software. Commercial software quite good, user-friendly. But if you put rubbish in, you get rubbish out. So again, it doesn't matter how cool and sophisticated your tool is. If behind the tool there's no brain, it won't work, okay? And this is a good transition for my next snapshot, which is the metocean. So metocean is one of the key input for any offshore operation, okay? And having that wrong, it means that you're basing all your approach on the wrong foundation, okay? So what is metocean? Metocean represents all the information, statistics about the sea state, the waves, the current, the wind, which are used for the design and for the planning of the construction. Now, we also need to keep in mind that metocean is very different when we're talking about offshore and nearshore, okay? And I've seen in my experience that a lot of time we know a lot about the wind farm because it's the most important asset, but we know little about what's happening at the nearshore where I have to pull my export cable, okay? So, and I found that, things are improving in the industry, but this part until a few years ago was very much, let's say, disregarded. And I will just show you an example of how this can impact on your project, okay? So typically, if you want to know what's happening near shore, I need to do some modeling of the wave propagation, the current, and using a quite sophisticated tool. Now, I take an example I worked on a few years ago, okay? Here we're talking about on-bottom stability of cable, which is, again, quite not topic. So in this case, the client had to leave a cable in wet storage for 1 year, and we had to verify if it was stable or not. So when I'm coming back 1 year after, will I find my cable in the same place and will be okay? So based on DMV, we had to test it with a 10-year return storm because of the risk level. And the only information we had at the time was the 10-year return storm offshore. So we're talking about 7-meter HS, we translate in almost 14-meter maximum wave height, okay? And we had to prove the stability of the cable here, where I have between 8 and 15-meter water depth. So as you can imagine, 14-meter wave in 8-meter water depth, is that possible? Not so. The other problem was that the main predominant direction of the wind farm was from north to south. So if you see, very perpendicular to the cable. Result, we applied the DMV guideline, cable was not passing, okay? Solution, let's mitigate by installing a lot of rock bags, which cost a lot of money, and most likely they introduce other risks, because every time I install a rock bags, I might damage the cable while I'm installing the rock bag, or later on, when I'm removing the rock bag, I might damage my cable because one of the rock might drop. So what we did here was to convince the client to, look, let's make a study to see how the offshore wave propagates near shore and see if we can get any benefit from that. This is what we did. And in the end, what we prove are two important things. First of all, there is a drop in height. So the wave height was dropping even 65%. So from 7 meter, we got more around 3 meter, okay? And secondly, there was a big change in the direction. So the direction is getting more and more perpendicular to the shore, which means that it's more parallel to the cable. As a result, we try again the DMV on-bottom stability analysis, and we come out that everything was passing. So our clients saved millions in mitigation, which were pretty useless, okay? So again, spending a bit more money in engineering can really have a big benefit for the project. So just to conclude very briefly, so subsea cable failure can have a big impact, and it's quite important that proper engineering is carried out, and proper engineering can only be carried out by experienced people. So my suggestion would be not to be too cheap in the engineering phase, because it really pay out overall in the construction of the project. So that's me. And of course, if you want to visit us later, that's our booth. And thank you so much for listening today. Okay. It's okay. Any question? Akim, any question? No? Was too clear, maybe? Okay, fine. Thank you so much. Bye.
Mm-hmm.